Okay, so I want to talk about these two kinds of statistical inference. Um, so there's Bayesian and there's frequentist, and I think of there really being only two kinds. It's been about 100 years now of argument about these two kinds, and there's been lots of attempts to have other kinds, but they really haven't emerged. There's kind of, little small kind of schools around some maybe other styles, but these two really, really do dominate, okay? And it's kind of a grad level, but not even grad level. It's kind of a maturity to kind of understand there are these two perspectives and to be aware of them and to be aware that they're not really like either one or the other, okay? And they're both useful, but they're different. And I think of this as like waves and particles in physics. If you ever did any quantum physics or, chatted about quantum physics late at night with friends, you learn that, things like electrons and, protons, whatever, they're actually both waves and particles, photons. They have wave-like behavior and they have particle-like behavior. And those are kind of complementary. They allow you to infer different kind of things, but they also conflict. They don't really quite work together. And that's just a fact of life. You just have to accept that nature is a little more complicated than our human brains are quite able to cope with. And that's true about inference too. So inference is a non-trivial thing. What you folks are learning about in data science and statistical inference is non-trivial. It's about how to try to figure out the truth in the world just based on partial observations. Very mathematically non-trivial. It's taken human beings a long time to start to develop any way to think about that at all, okay? So the Bayesian and frequentist are really the kind of the two ways to go about this, and they are both valuable. I use both in my own thinking all the time from any given day. Most statisticians are a little bit of both, but like 40 or 50 years ago, that was not the case. You were either one or the other. The Bayesians and the frequentists were fighting all the time. So I want to give you a sense of what kind of the fight was about, but also not just the fight. I want to give you a sense of what the issues are and to help you think about a little bit, maybe I'm a little more of a Bayesian, or maybe I'm a little more of a frequentist, kind of because of the more really the kind of problems I like to solve. What does that really mean? Okay, so let's try to do this thing. So this will be a little abstract, but it's just like waves and particles in physics. The first time you hear about it, you're not going to quite understand it, but you need to hear about it. And later in life, you'll start to get more and more clear about it, hopefully. So frequentism, first of all, what does frequentism mean? Well, it means frequency. It means occurring multiple times. So if you're a frequentist, you want to say that some procedure works on average, meaning if you like write a piece of software to do this procedure, it'll work every time someone runs the software, okay? You're not going to just run the software once, and I will guarantee you that it'll work no matter, whatever kind of problem you run it on, okay? That's kind of the basic idea of frequentism. I think, writing a piece of software is a nice way to think about this. And so you gotta think though, where does the randoms come out? When you're talking about an average, it works on average, what do you mean? And roughly speaking, what you mean by average here is just that if you get multiple data sets and you run your procedure, you get some answer, and now do that again and do it again. Now you wouldn't really do this in real life probably. You just want to run your data set, get one data set and run your procedure. But if conceptually you're thinking about running it again and again and again, and it kind of works on average over all those runs, that kind of gives you some reassurance on your particular run that it's going to be, it'll work, all right? And again, that's maybe not as convincing as it should be, or maybe not that convincing, but I think if you think about this as writing a piece of software, you want to be able to give a frequentist guarantee that on average it's going to work. All right, so this idea is really going back to the 20s and 30s of Neyman, who started the stat department here, Abraham Wald, who was both an economist and statistician, and others. That's the idea. Now, in the FDR, that's exactly the kind of expectation we had. It was a frequentist expectation. It said, you take this FDP, which is a random variable. It depends on one particular data set, right? And you take its expectation, meaning you're going to look at doing this whole, this BH procedure or some other procedure, conceptually at least, again and again and again on multiple data sets. And you want on average for the procedure to work well. That's what it means to have FDR control. It's a frequentist assertion. Okay, Bayesianism, very different in some ways. It doesn't really start with, on average, the procedure works. It just sort of says, what do you do when you get data? Well, you use probability theory because everything's uncertain. Right? So you say, okay, what do I not know in nature I'd like to know? Let's call that theta. So it's sometimes called a parameter, sometimes it's a prediction, sometimes it's a model. It's what I was calling reality before. Okay, so let's now call that theta. So what's the probability of reality or some value theta given the data? That's what you'd really love to know, because now you're going to get some data and you'd like to update your probability. And we use Bayes' theorem here, which says, well, that's proportional to the probability of the data given theta. That's usually called the likelihood. It sort of says, given the data, how likely is the value of theta? That's not the same as the probability of theta. It's kind of the backwards probability. All right, and then we multiply that by the prior on theta. So a Bayesian, to use Bayes' theorem, has got to write down a prior on theta. All right, the frequentist tries to avoid writing down a prior. They just don't want to think about a prior. And they avoid that by saying, well, I'm not going to think about just one experiment where I would need to write that down. I'm going to think about doing this conceptually again and again and again. Okay, and that kind of allows you to get around the prior. All right, so think of this little equation now, not just as a piece of probability theory, but think of it as an updating of, the belief kind of thing. Before you saw the data, you had a belief about the state of nature, or the, theta. All right, you got some data and you updated that into a new probability of theta given the data, and you keep going. You can do this again and again and again. And so, there are a lot of people kind of think that humans do something like this, and then people argue about that and so on. So a Bayesian never wants to talk about averages over other possible data. They just want to say, given some data, condition on the data you got, and update the parameter, and then make some plausibility arguments. That's the right thing to do with, beliefs. Okay. Averaging over data would be anathema to a Bayesian. They would say, why are you averaging over other data? You didn't get that data. Why should you average over it? You didn't get it. So don't try to imagine thought experiments that you got it. You didn't get it. So just condition on the data that you got. But to condition on data, you got to be willing to write down a prior. And so this is where the frequentist sort of says, well, we agree with that argument you made, but we want to find another way to do statistics. Bayesians are happy to assign probabilities to things that can't be repeated. Okay, the probability that something is destroyed. Right? If it's destroyed, it's destroyed. You can't do it again. But also things like the probability that Biden is going to win against Trump. All right, all of us have a probability. I have my own, and we all have kind of a subjective probability, because I have a different belief about theta maybe than someone else. And so given my beliefs about the current state of the world out there, I now start to collect some data and I update it into my current belief about that election. Right? And that election is not going to be repeated, God forbid. And so it's not really conceptually clear what you would mean about a frequentist. Conceptually, I'm going to repeat this again and again and again. It's just not very clear. Okay, so let's think specifically about hypothesis testing. That's one kind of statistical inference, not the only kind. So frequentist hypothesis testing is what you learn in the classical stat classes. It's the type 1 error, the type 2 error. It's the language of the null hypothesis and the alternative. If you collect data that doesn't fit the null, you reject the null. And you ask to control the probability of a type 1 error. Right now, earlier we've been talking about type 1 errors as just your false positives, the number of false positives and all that. That's just a random variable. But when I wrote down probability of a type 1 error, okay, a type 1 error is an error. It's a 1 or a 0. So the probability of an error is the same as the expected value of that 1 or 0. Okay, so this is an expectation error. This is a frequentist probability. All right, so it's a probability of a type 1 error if you were to repeat this hypothesis test again and again and again, the same hypothesis test again and again. Okay, so that is the actual Neyman Pearson full framework, is to write down, hey, I'm going to control the probability of the error. All right, and the lemma that we've talked about in the homework is a lemma that proves how you can get control of that, and conceptually, if you were to repeat the experiment again and again and again. Okay, so that is frequentist hypothesis testing. Neyman Pearson is an example, and this is what you will have learned in your previous classes.
Hey, Professor, there's a question in the chat.
Yeah, please.
By Ying Han, he said, what does it mean that multiple data sets are not observed data?
Yeah, frequentist doesn't say I'm going to collect a whole bunch of different data sets and I'll do inference over that. That's like the multiple testing thing we've been talking about. And the multiple testing, both the Bayesian frequentists have their own approaches to that. Okay, Benyamini-Hochberg is a particular frequentist approach to that. Okay. That's where your data is all the multiple tests. But even there, you would say, I would gather all these multiple data sets, and then I would do that whole thing over again. And here I'm imagining, it's a thought experiment. I'm imagining what would happen if I were to do my whole procedure over all the data I got again and again and again and again. would it be the case that some error rate is less than some like alpha value? Okay. So it is a thought experiment kind of situation. It's not a collect actual data kind of situation.
Wait, Professor, I'm a little confused. Since you said to collect multiple data sets, so those are actual real data, or are those kind of hypothesized data?
No, it's let's call it imaginary data or thought experiment data. That's what a frequentist is doing. When you write down a Gaussian model and you say, I sampled out of the Gaussian model n times, and then I got a standard error of the mean or a bias and variance. Those are fluctuations you would get not just on one data set, but if you were to do this again and again and again. Okay, and and you're not doing it again and again. In real life, you're doing it only once, right? And you're trying to say, given I did it once and I got an answer, that's the way I got that answer. If I were to do that again and again, would I on average get the right answer? At least that. It still doesn't tell me I got the right answer, but it says at least gives you reassurance if you were to do it again and again and again, you're on average correct. It's a weak assurance, but it's an assurance. Okay, so frequentist is a thought experiment kind of situation.
Is the prior probability on line 3 in this case just p theta?
Is the prior probability on line? Yeah, p theta is the prior. That's correct. And the likelihood is the p of data given theta, and the left-hand side is the posterior. The p of theta given data is called the posterior.
And p theta is just basically like the probability of the null.
Not the exactly in the hypothesis testing situation, it would be for example the probability of the null. Exactly. Right. So coronavirus situation. You could say I come into the coronavirus situation knowing nothing about the probability of the null. I'm just going to run some Neyman Pearson test, and I'm going to guarantee that no matter what the probability of the null is, I'm not using the prevalence. Remember that? It was just sensitivity and specificity. That I'll make some guarantees, right? Mm-hmm. And now I come into it as a more of a Bayesian person. I say, but wait a minute, I have a prior belief that's pretty strong about the probability of the null. I think most people don't have the coronavirus right now. Okay, it's like the prevalence is less than 0.01. So can't I use that in my once I get some data? Shouldn't I use that? I certainly believe I should use that in the case of like my own individual medical testing. I think I have a certain probability of having the plague right this moment, pretty low. But I could go in and do a test tomorrow, and it could be a false positive. The test didn't work correctly, the temperature was wrong or whatever, and so they could, based on the data from me, they could say, oh, you got a result which is if you had the plague, you would get a positive result here. You got a positive result. I'd say, okay, fine. That's the p of data given theta term. That's large, but p of theta is so small that I'm not worried. My posterior is still small. Okay, so that's where you're using a prior when you really, you should be using a prior when you have a good reason to believe you're prior. And you do. And so Biden, Trump, each one of you has a pretty well-informed prior about that. And if you're really trying to make money off of that or whatever, decide where to live, you should probably use that prior in making your own judgment about what's going to happen. Okay, so in these kind of one-off things, also I'm often a Bayesian when I'm working like with a biologist or somebody who knows a lot about their problem. And you come in and you say, what's the state of nature? Well, it's like, how does DNA go into RNA and particular kind of binding, blah, 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 blah. And I can say, okay, that's the current belief about the state of nature. That's a P of theta, what the biologist currently knows. Now I'm going to collect some new data, and I'm going to get a new theory based on the extra data I've gotten. I'll have a P of theta given the data now, the new data. All right. And I should have started with kind of the current existing knowledge. I shouldn't have just said, I'm going to do a hypothesis test based on no knowledge whatsoever of biology. Okay. So I think of kind of biology and kind of heavy knowledge intensive sciences where you're going to do one test, you should use all your knowledge, and Bayesian is pretty reasonable. I think about frequentist is very reasonable where you're just going to write a piece of software and tons of people out there are going to use it for any purpose. And maybe not just for the coronavirus, but for any virus, the flu, the whatever, they're going to use this kind of procedure that you've written down. And well, the flu has a very high prevalence and the coronavirus doesn't. And so you should be not taking into account the prevalence. It should just work independent of that. And so frequentist thinking makes sense there. Is that helping?
Yeah, it helped a lot. Thank you.
All right. So I probably won't finish today, but that's always good. That's a sign that we're all thinking out loud together. Okay, so Bayesian now applied to hypothesis testing. Indeed, the probability of the theta, that's just the probability of the null. And that's just like one number, but it's a pretty important number. we've talked about prevalence. Okay, so this is actually what I was just saying, kind of, all kind of written down on a slide. Here's kind of comparisons, the waves and particles of physics being in statistics. The Bayesian perspective, it's conditional. You should make inferences conditional on the actual observed data, not on possible data you could have observed. All right, you tend to be an optimist as a Bayesian. You say, okay, I already have some beliefs. Let's optimistically believe they're not too unreasonable, and let's make the best use of our sophisticated probability machinery. The frequentist perspective is not conditional. It's not trying to condition on the data you got right now, typically. It's trying to be unconditional. It says on all the possible data you could get, unconditionally, are you doing well? Okay. I think of it as natural when you're writing a piece of software that'll be used in many situations. And I think of it as kind of the pessimistic perspective. It says, let's don't trust our basic background knowledge. Let's don't trust, lots of things. Let's just make a procedure that doesn't make many assumptions and protect ourselves against making a bad conclusion. Okay. Now, here's a question for you. You all heard about bias and variance, hopefully in the previous classes. All right. Bias and variance, are those frequentist or are they Bayesian? Are they both? Or are they unrelated to frequentist and Bayesian? Well, let me take a 30-second pause here. And I'm not going to look at the, I'm going to keep sharing my slides. I'm not going to look at the chat section. But why don't you raise your hand if you think that bias and variance are frequentist, and don't raise your hands if you think it's Bayesian. It's a terrible way to do the test, because if you don't know, of course, we're going to think you said Bayesian. Actually, I'm going to really do it. So I want, yeah, actually, I get to see lots of raised hands. I don't see names, but raising of hands. Okay, so a lot of people say bias and variance might be frequentist. Okay. Let's just stop there. And if you raised your hand, great. Unraise your hand now. And now, if you think that bias and variance are Bayesian, raise your hand. Just get a rough feeling for how many people think that's the right way to think. Okay. Okay, so that's great. Okay, so turn off your raising of hands. How many of you think now that it's both, really, bias and variance are both frequentist and Bayesian kind of concepts? Okay, good. I'm getting lots of responses. That's great. Okay, so go ahead and shut that off. Okay, so I'm gonna actually go through this next time a little bit. So bias and variance are really frequentist. Okay, they have expectations in them. Variance in particular. Bias does too. They have expectations, and those are frequentist expectations. Okay, so there's you could use the words bias and variance in all kinds of ways, and I don't want to say this is the only way, but this is kind of the classical way that those are frequentist expectations. We'll talk a little bit about that next time. Okay, so what I think I'm going to do is actually do these next few slides next time. Here I'm going to be giving you a little formal framework of a full kind of decision theoretic framework. How do you make decisions of uncertainty formally? I'm going to show you that there's kind of two approaches, and they're Bayesian and frequentist. So we're going to kind of give almost a mathematical reason for why there's maybe two approaches and only two. So I'm going to go through this next time, but you're welcome to look through the slides here and sort of see about what we'll be talking about next time. And to finish up, I want to give you a nice little cute thought experiment. All right, and we'll probably maybe even end a couple minutes early. Okay, so this is going to compare Bayesian and frequentist thinking. It's going to be a little bit of a cartoon, but it's a thinking thing, okay? So let's suppose you want to estimate the average height of the population in a city. Okay, so it's a really big city like San Francisco, New York. You can't actually go get the height of everybody, so you want to take a subsample, something like go get 100 people randomly sampled, and you're a good data scientist, you really do a random sample in some way, all right? You're going to measure their height. Let's call that xi for the ith person. All right, and then we're going to try to get an estimator of the underlying population height given the data. All right, and we could either be Bayesian or frequentist here. In either case, we're going to need some kind of a probability model to be either Bayesian or frequentist. So let's assume the model is that the height is coming from a Gaussian distribution around some population height, mu. So that's the thing we'd like to estimate. What's the population height? With some kind of variance. I just called it 1 here just for convenience. Let's call it, if you want to call it sigma squared, that's fine. But I don't want to estimate sigma squared. Let's just have it fixed. Now, normal distributions are actually quite reasonable for as a probability model for height. Because if you think about what height really is, It's just all the cells in your body as you were growing up. One cell divided and led to another 2 cells, and then those 2 cells became 4, and so on and so forth. And that happened throughout your body. So your total height is actually the sum over a huge number of small stochastic events. And that's exactly the situation where the essential limit theorem is appropriate. Okay, so a Gaussian model here is actually quite reasonable. All right, so now let's be a frequentist for a moment. A frequentist says, okay, I got a Gaussian model, I want to estimate the mean. Let's talk about an unbiased estimator of the mean. And now bias is a frequentist constant. I'm going to talk about an unbiased estimator, and hopefully you would know how to do that. You would write down the bias actually, and you would maybe see that it's frequentist. And you would find out that X bar, the sample mean, is unbiased. What that means is that its frequentist average, expectation of X bar, is actually equal to mu. We'll talk about that next time, but that's what that means. Okay, so unbiased estimator of mu is X bar. So you should use the mean. It's a very good frequentist estimator. It has this nice property. It's unbiased. All right. So you use it and you get like a number like, 5 foot 8 inches or something like that. Okay. Now someone comes and says, oops, I'm sorry to tell you this, but the measuring device we were using to measure people's heights was broken. And actually anybody who's over 7 feet tall was actually recorded as only being 7 feet. It truncated, right? It couldn't record anybody 7 foot 6 inches. It recorded that as 7 feet. Okay. Now that's certainly worrisome when you had to collect all this data and do all this analysis. But now it turns out that in your actual data, there was no one over 7 feet tall. In fact, there was no one even over 6.5 feet tall. Okay, so this actual worry that there could have been a broken device is not really meaningful here, okay? Now, if you're a frequentist, a really good hardcore frequentist, you would say, okay, that was the wrong model. Gaussian around the mean is wrong because I have a truncation going on. I have what's called a truncated Gaussian. It goes up as a Gaussian bump and then it truncates off. That's the actual probability model for my data, all right? And under that probability model, X bar is not an unbiased estimator of mu, but there is an unbiased estimator of mu, okay? It turns out you can figure out what it is. It's not that hard. And you can find out what it is, and it's not gonna be X bar. So if you're a good frequency here, you should adjust your data, your estimator, and so whatever, 5 foot 8 inches is not correct anymore. It's gonna be a little bigger than that, turns out, okay? But there was nobody over 7 feet tall, and there was no time, this thing, it was irrelevant, right? Okay, and now if you ask about the Bayesian here, the Bayesian will not alter their estimate, okay? We'll talk a little bit more what a Bayesian estimate would mean here, but for example, like posterior mean. Why? Well, because it just conditions on the data. It doesn't care about other data you could have gotten if you didn't have a broken machine. All right, that's another experiment, but I didn't get that data. I got this data, so I condition on that data, and it has everybody 6'5" and below, and then I do some operations and I get an answer. I'm not going to change that just because you said it could have, it could have been a problem. It wasn't a problem. All right, so I would argue here personally that the Bayesian perspective actually here makes more sense, and this is not uncommon. The kind of logically and conceptually, the Bayesian has got some nice virtues. All right, and kind of the only problem really with it is that darn prior, is that in some cases you just don't have any idea how to set it. And if you set it in some kind of arbitrary way, you could just get a kind of a crazy answer, or you could get one that you believe that no one else should believe, right? So you just have a bit of subjectivity. And so the field kind of comes together when you sort of admit that. You say, the Bayesian approach is really nice and clean and all that, but I gotta be a little careful. And so when you start to be careful, you allow yourself to bring in frequentist thinking. All right, so now we're on to the new stuff for this week, and I am gonna go grab my phone because I don't know exactly what time it is. Just give me a second to go grab my phone. All right, so let's talk a little bit about formal framework for Bayesian and frequentists. Let's talk about decision theory, and I have to kind of talk about decision theory in this class because it's a class about decisions. And so you should know what when people are talking about when they say decision theory. But this could be a little dry, so I am trying to come at it from, we're going to use decision theory to really make formal the idea of Bayesian inference and frequentist inference, and then we're going to see how we can start to relate them a little more. Okay, so I hope you kind of appreciate it as I was going through that both Bayesians and frequentists need probability models for the data. If you don't have that, you're just starting from sort of nothing. It's ad hoc. You can't say anything about what you're doing. You can't be mathematical. So we do assume that you have a probability for the model for the data. That often comes in the form of a P of X, given theta, or P sub theta of X. okay? So it's indexed by a parameter theta. When I say index, that means I've got a lot of possible probability models for my data here. I don't know which is the correct one. And so as I run over some parameter theta, I'm indexing into the class of probability models that I'm considering as the source of the data X. So I want to find out which one of them is the one that generated that. So once I see some data, the data is observed, I define a procedure, which here I'm going to be calling delta of X. Delta of X could be compute the sample mean. X can be a vector of all of the X1 through X100 or 1000. It could be a matrix. X can be anything. It's the data. It could be an image. It could be speech. And delta of X is just a function that applies to that data. So you could write a little Python function that takes in some data, outputs some number or some mean or some variance or some list or whatever it does. I don't care. Theta is a procedure that takes data and maps it to something else that we often call a statistic. But don't worry about that. It's just a procedure that operates on the data. All right. Now, most statisticians would agree you need a model for the data, you need a procedure, and they will also agree that you need something called a loss function. Because you got to evaluate how well you're doing. And evaluation is really important, and you have to be clear on how you're evaluating. So in statistics and more broadly, economics and lots of related fields, you talk about loss functions. A loss function is just a function of two arguments. It's a function of theta, which is this index that tells you which is the probability distribution that generated the data. So there's going to be a piece of theta, okay, that is generating the data, and I don't know what theta is, all right, but there is some theta that generated the data, all right, and given that it generated the data, I'm going to get an X, which is my data, and then I'm going to make a decision based on X, which is delta of theta, all right. And so now I've got everything is all done. I got my data, and what I can do is now say, well, how happy am I with that result? Now, I don't know theta, but let's imagine the supreme being is kind of looking down, and the supreme being does know theta and does know what I did, my delta of X, and can look and say, well, that was kind of a dumb decision in that setting. Or it can say, hey, that was a good decision. And L measures that. It measures, if I were to know what theta was, how happy would I be with the decision I just made? All right. And I hope you can sort of already see that our little 2x2 table is an example of this. Theta would index the rows. It would be a 0 or 1. It's the reality. And delta of X would index the columns. It would be a 0, 1. It's the decision. And the entries in those cells of that little matrix are the loss function. They're the L. Once you tell me what row you're in and what column you're in, I know what cell I'm in, and I can tell you how happy I am. And the numbers we've been putting there so far have been ones and zeros. You're happy if you make a true positive or a true negative. You're unhappy if you make a false positive or a false negative. And happiness means a 0, and 1 records a unhappiness. So it's a loss. L is it's bad to have a positive number. All right, so that's an example of a loss function. It's a 1-0 loss in this case, and it's a function of the little 2x2 table. And the two arguments of the loss function index the rows and the columns. But now you can do this more generally. Theta can index any class of probability distributions, not just 2 of them. And delta can index any class of decisions, not just 2 decisions. And then the loss can be any function of the state of nature and the decision you made. All right, so here, just to be really clear, is my example of the 0-1 loss. So I had theta being a 0-1, that's my rows. I had delta being a 0-1, that's my columns. That's the language I was using earlier, and there's my little table. And now in each one of those cells, we can put a loss. What's the loss you feel if the truth was 0 and you said 0? Well, we've been until now saying, loss of 0. I'm just happy there. I don't feel any loss. And in the upper right cell, that's a false positive. We've been putting a loss of 1 there, the count of the number of errors. Right? But we could put other losses in here. You could be really unhappy to make false positives and put a 10 in there, and not so unhappy to make false negatives. You could put a 1 in the lower left cell, for example. That's a false negative. Okay? Or vice versa. Or you could even put some non-zero numbers in the 0 in the correct answer. Maybe there's a cost you pay just to play the game or something like that. Losses can be whatever you think are appropriate for your problem. All right, and in particular, we could put 0s and 1s in there like we've been doing so far in the class. Here's another loss that all of you have seen, I'm sure, in your previous classes. This is the L2 loss, or the quadratic loss. So here, theta is not a 0, 1 at all. Theta is a real number, okay? Ranges from -infinity to infinity, Okay, and so it like might be the mean of the Gaussian, and you're trying to estimate what's the mean of the Gaussian. That would tell me what parameter, what particular probability distribution is generating my data if I knew the mean. All right, and I'm going to make a decision, which is probably not going to be a 0 or 1 in this case. It's probably be maybe an estimate of theta. We would often call that theta hat. But theta hat is a function of the data. It's a function of x. And so here I'm calling it delta of x. All right, and it might be an estimate of theta. Doesn't have to be, but if it is, it's very natural then to use the L2 loss. I take the difference between my estimate delta of x and theta, all right? And ideally that's 0, so I square it to get a positive number and kind of emphasize the big errors, and I call that my loss, all right? So you can't think of a 2 by 2 table anymore. You can sort of think by an infinite by infinite table where all the possible values of theta are down one side and all the possible decision went down some other side. And now you kind of have a little quadratic bowl shape kind of rising up above that little table. All right, so there's a couple of loss functions, and you can think of all kinds of other loss functions. Okay, there's like many of them, and really good. It's an art to pick the loss function, and you don't just pick these textbook ones. These are the ones you learn in school. But if you go to say Amazon.com, or other companies, people are writing down all kinds of more rich losses about how unhappy will customers be if I offer something on sale and they don't get it, or they can't do a return. How unhappy will they be tomorrow versus 5 years from now, et cetera, et cetera, et cetera. How unhappy will people be if they see that we're cheating in some way, or et cetera, et cetera. There's just all kinds of thought that goes into loss functions, and so you need to know what they are. For us, they're basically a function of two arguments, one of which reflects a state of nature, what's really happening out there, and the other is your decision based on uncertain data. Now, with this framework, we're going to now use loss functions to compare procedures. In some setting, you might have a procedure which might be calculate the sample mean, and I have a different procedure which might be calculate the median. And who's better, me or you? Okay, well, you have to have some way to compare. You can't just assert that I'm better because I'm a professor, or you're better because you're younger. So we have to have a loss function which allows us to compare. Okay, so if my loss is smaller than yours, in some sense, then my procedure is better. And if we agree on the loss function, that's just we have to agree with that. All right, but now we run into a problem, which is this loss function is well defined. Maybe it's quadratic or 0, 1, right? But how do we use this in real life? Because we don't know theta. That's the whole point. If we knew theta, we wouldn't be doing statistics. All right, and x is random. It'll take on different values on different trials. So L of what? Where do we plug in for these things? One's unknown and the other's random. All right, how could we compare things if the arguments aren't even known? All right, so now you start to get into the deep issue of that people started to face kind of in the 1930s, and this arguments still go on to this day about how to do this. How do we develop a formal framework for statistics? All right, so since we have an object here which has got some unknown arguments or random arguments or both, all right, well, we have to, in some sense, average over those values, okay? We have to somehow combine the different possible values. Maybe not just a classical average, but in some sense, we have to take some kind of an expectation. We have two arguments here, and we can focus, first of all, on sort of combining over the different thetas, averaging over theta, or we could focus on combining over all the different x's you could get. Those are two different approaches, and those are precisely the Bayesian and the frequentist approaches. The Bayesian is going to take an expectation over theta, because theta is a random variable for the Bayesian, so you can do that. The frequentist is going to take an expectation over x, because x is a random variable from the frequentist point of view, and you can take an expectation over the x. So that's what's going to happen. When we write down an expectation over the loss function with respect to x as the random part, all right, then I write it in this way. So E sub theta there is the probability distribution. It's the expectation under the probability indexed by theta. Remember, theta was an index over all the possible probability distributions I'm considering, maybe all the Gaussians with some mean unknown or anything, and theta indexes those. So I take the particular one indexed by theta, I use that as my probability to do the averaging. And then I do the expectation, the averaging of the loss. The theta inside the loss function is the same theta. I don't change thetas. It's exactly the same that index the probability. all right? And I take an expectation over the X part. So the loss is random because X is fluctuating randomly under this theta distribution, this P of theta. And I use that P of theta distribution to average over all of the choices of X and get an average loss. All right, that average loss is very, very important quantity. It's called a risk function, right? It's not a risk just by itself. It's not a Bayes risk, which people sometimes mistakenly call it, all right? It's a risk function. Why is it a function? Because it's a function of theta. Because I did this for, I don't know what's the right theta. I'm going to do it for all possible thetas, and I'm going to get a risk function. All right, we'll show you a risk function in a minute, but it's a function of the unknown theta. All right, so that's going to be that's a bit troubling. And Wald, back in the 30s, already was kind of aware of this as a problem. He was looking at this and saying, well, how do I compare two procedures? Some people's procedure might be better for some theta. Other people's procedure might be better for other theta. Okay, and that is a core issue that's still being talked about to this day. There are some procedures which are just always better than some other procedure. Sometimes you can compare two procedures and one of them is better for all theta. Okay, that does happen, and that allows you to rule out the procedure which is worse, which is beat by some other procedure. Okay, and so a lot of statisticians for quite a long time trying to find ways to rule out procedures because they were always uniformly worse, uniform in theta, than some other procedure. Right? But it doesn't happen enough. There are still cases where some procedures are better for some theta and others for other theta. Okay, and frequentists have to then talk about that. All right, the other way you could go, we'll talk about that some more in a minute. But anyway, I hope you now understand what the risk function is now. It's sometimes written as R of theta. Okay, the other way you could go is you can say, well, no, I'm not going to average over the X, because that's kind of averaging over other data I could have gotten, but I didn't get. And I don't kind of like that. And you can imagine this is a Bayesian talking, saying that. And so what are they going to do? Well, they can say, well, I'm not going to average over X because I'm going to condition on X. I'm going to fix X. And that kind of gets rid of the problem, at least a little bit there. I'm not looking at multiple X's. I'm looking at the X I got. But I still got the theta to worry about. Which theta? But the Bayesian has a prior on theta, P of theta, and has a posterior on theta, P of theta given the data. So the Bayesian can take an expectation of the loss function with respect to theta now. So that E doesn't have a sub theta there. That E is a conditional expectation, conditioning on X, of the loss function where theta is the random variable. All right, so this is called the Bayesian posterior risk. It's different from the risk function on the left, the frequentist risk. Okay. So this thing is effectively still a function of X, but we got rid of the theta part. And the frequentist, he or she has a function of theta, but they got rid of the X part. All right, so both of them at least made some progress into getting something you could start to compare between procedures. All right, so there was the frequentist averaging over the delta of X, and there's the Bayesian averaging over the theta. All right, and here I've summarized all that on this page. The risk function, if you're a frequentist, is the expectation under a fixed theta of L of that theta delta X, looking at all the data you could get. The Bayesian writes down the posterior risk. It's a function of X, and we've averaged over the theta.
Hello, Professor.
Yes.
I have a quick question. So for the frequentist risk, what's the subscript like theta means? Because you said it's a function of X, then why do we do like E sub theta?
Okay, the frequentist risk is not a function of X because we've averaged over the X. That's the expectation is an average over some random variable. The random variable here is X. Okay. E sub theta means that when you take an average, you have to use a certain probability distribution, right? All right. Which distribution do you use? We have a whole bunch of them here. We have a whole family of all indexed by theta. So if these are a bunch of Gaussians with different means, theta could be the mean. And so should we use the mean of 2 or 0 or 1 or -1? What mean should we use? And the answer is we don't know because we don't know what the true mean is. So we do it over all possible theta. And so E sub theta means take the average with respect to the probability distribution indexed by a specific theta. Now we get a single number, because after we take that expectation, we get a number, right? And we did that for that theta. So the overall result is we got a function of theta, which we call R of theta.
Also, it's for a list of indexes, which is
Yeah,
Yeah.
think of all the means of a Gaussian. I have a one-dimensional Gaussian on the line, just a little bump, right? And I can shift it along to all the different places the mean could be, right? And for each one of those places, those theta values, right, I have a distribution. It's a little Gaussian there. And I can compute my loss for that theta under some data that I got, right? And I can do that again. I can do that, you know, for drawing data out of my distribution, okay? So I can do this for a delta of x being the sample mean, for example, that takes the data and forms a sample mean. I can do it for delta of x being the median or whatever. I get a number for each theta.
okay. Got it. Thank you.
I'm going to do that in a moment with the L2. So you're going to actually see a concrete example.
Cool. Thanks.
Okay, now if we go back to this slide right here, we started with a function that had two random arguments. Certainly a Bayesian thinks of them as both as random. And we took one expectation of one of the arguments. You may remember from your calculus class, there's a theorem called Fubini's theorem that says if you want to take an expectation with respect to two random variables, a function of two random variables like f of x, y, right? You can do that, and you can do it in either order. You can take the expectation over x first, and then y, or over y, then x, and you'll get the same answer. That's Fubini's theorem. So actually, if you take the frequentist expectation there, which is a function of theta, R of theta, and you take an average over the Bayesian posterior, which averages over theta, you'll get something that's just a number. It doesn't, we've averaged over both the x and the theta. Or you could do it in the other order. You could average over the Bayesian posterior, which we've done on the right there. We've averaged over the theta. We get an object which depends on x, and we can now average that over x, the marginal distribution on x. And we'll get a number. And those two numbers will be the same because of Fubini's theorem. And that number is called the Bayes risk. So it's kind of a hybrid. It's not really either Bayesian or frequentist. It's kind of both, but neither people are comfortable with it really. The frequent doesn't like as you average over theta. Bayesian doesn't like as you average over x. But both of them see some value in the other framework. So the frequentist might say, well, we averaged over theta. I don't really believe in priors, but I do kind of think that some thetas are more important than others. So I think of it kind of like a weighting function. All right, and the Bayesian, you know, similarly might say some x's are more important than others, so I'm maybe okay for some averaging. So the Bayes risk is what that quantity is. All right, and I had that as a fun little bonus exercise here, just to sort of use Fubini's theorem here and make sure that the conditions are satisfied, and you can do that. Okay, so let's do this for the frequentist risk, all right, under the L2 loss. So there's my L2 loss, squared error. All right, so I'm going to calculate the risk. The risk is the expectation of the loss for a fixed theta. So theta is not going to be varying in any of this. It's going to be just an index, if you will. It's a particular fixed choice of a parameter. All right, so there's the definition. Risk is the expectation of the loss. Then I'm going to plug in the specific loss we're working with here, the L2 loss. So now we got a nice little quadratic instead of L. All right, now I'm going to do a little trick that is very common in statistics. You've hopefully kind of understood it or used it. It's really kind of a geometric trick. It's the Pythagorean theorem, really. We're trying to compute the expectation of a square. That's kind of like c squared is equal to a squared plus b squared. All right, so we would need to kind of find what's the a and the b. All right, so what you do is you subtract something and add the same thing. Okay, if I subtract something and add the same thing, I haven't changed anything. So that's something that I subtract and add is just the expectation of delta x, okay, under this particular theta distribution, p of theta, okay? So expectation sub theta of delta x is just a number. You know, it could be 5.2, it's just a number, right? So I can subtract it and I can add it, and I haven't changed anything, okay? Now in classical Pythagorean theorem style, we can now square this thing out. Take the first two terms, put them together, square that. Take the second two the last two terms, square that, and then look at the cross product. So I did that in bloody detail here, and I doubt that I got all the parens right and all the brackets, but maybe I did. I think I can already see one error there. No, that's not an error. There may be no errors. That would be a miracle. Anyway, I took the first two terms, delta x minus e of theta delta x, and I squared that, took its expectation. That's the first thing there. Then I took 2 times the cross product of those 2 terms, each of which involved a subtraction. And then the third term, the last term, I squared that, okay? So I did a little expanda quadratic, high school or middle school. Now I need to calculate a little bit. I can calculate some expectations, which you should be able to do by this time in your career. So let's calculate some expectations. And what I'm going to do is worry first about that cross product term in the middle. It's ugly. Is there any chance it can vanish? And the answer is yes, it vanishes. Okay. So here's that cross product term, 2 times the expectation of, the delta minus expectation of delta times expectation of delta minus theta. All right. And in a longer class, I'd maybe have you take out a sheet of paper and try this yourself. I'm going to just go ahead and do this here. So what I did here is I noticed that second factor in the product, e sub delta of theta minus theta, that's a constant. Okay, because e sub theta of delta x, like I said before, that's just a number. I've taken the expectations. There's no randomness left. It's like 4.5. And theta is just a number, right? Because we're not treating theta as random. We're being frequentists. So e of delta x minus theta, that's just a constant. So I can pull that out all the way out in the front, outside the expectation. So I did that. I stuck it in between the 2 and the expectation. All right, and now I have 2 times the expectation of delta minus that expectation of delta. Now I bring the expectation inside of the brackets there. The first expectation hits the delta of x, and I get e sub theta of delta x. Then minus, well, I have expectation of that expectation. Well, that's just a constant. So that other expectation is vacuous, and I just get e sub theta of delta x. And now I have e sub theta of delta x minus e of theta of delta x. That's 0, and the whole thing is 0. All right, and so if you know anything about Hilbert space, random variables could be viewed as points in Hilbert space, and this is just orthogonality of certain random variables in Hilbert space. It really is just the Pythagorean theorem. Okay, so now I'm going to go back to this page, and I've just learned that cross product term in the middle, because of orthogonality, cancels out, and I'm just left with the first term, which I've just copied down below, and the second term, I've again noticed that everything inside the brackets there is a constant. E theta delta x minus theta, those are all constants. So that outside expectation is vacuous, and so I can erase it. And I get my final answer. And I give a name to these 2 terms here. The first one is called the variance of my procedure. My procedure is delta of x, takes data in and does something with it, delta of x. And I'm taking delta of x and I'm subtracting off its mean. E sub theta of delta of x is the mean of the random variable delta x. When I take a random variable, subtract its mean, square it, and take the expectation, that's called the variance. It's the variance of delta x, which I'm thinking of maybe as an estimator. In any case, it's just my procedure. So that's the variance of my procedure. The second term is the square of something inside the parentheses, and that something is called the bias. All right? We're thinking of delta x here as trying to estimate theta. That's kind of why we're using L2 loss. So it should be that when you take the average, when you take the expectation of delta x, you should just get back theta, okay? That's the idea of an unbiased estimator, okay? The expectation of the estimator is equal to the thing you're trying to estimate. It's kind of saying if you had infinite data, if you got lots and lots of x's, on average, you get the right answer. Okay, now this is not necessarily the case. It's not always good to be unbiased in this sense. This was kind of in the 40s or 50s. Everyone thought you should have unbiased estimators, and that's kind of dead now. It's a little hard for me to give the argument for it, but it's not entirely implausible. And so people tolerate a little bit of bias now. But why do they tolerate bias? Because they will allow, maybe a little bias will allow the variance to come down. Because we don't care just about the variance or the bias separately. We care about the overall risk. That's the thing we're using to compare procedures. We want the overall loss on average to be small. That's the risk. And we just found out the risk is composed of 2 pieces, the variance and the bias. All right. And so we want both pieces to be small, the variance and the bias to be small. All right. And so this slide's got a lot too much on it, but just let me kind of go slowly. Lots of frequent statistics involves analyzing the bias and variance of various procedures. analysis of variance, or, you know, some density estimator, or, you know, the median, and just all kinds of, you know, papers for decades have done that. Almost always you will find that there will be a trade-off between the bias and the variance. If you have some tuning knob in your procedure, you know, like in the Benjamin Hogberg, there was a tuning knob. In all procedures, there's some kind of tuning knob, some threshold of some kind. So if you adjust your tuning knob to maybe decrease the variance because your procedure is just too fluctuating, you know, it changes too much on slightly different data, you might want to decrease the variance in some way. When you do that, you will often make the bias larger. If you don't like the bias being large, you might try to cut down the bias in some way, but you will often increase the variance. All right, so you want to operate on some nice place in this trade-off. Classical statistics, again, formulated that problem as a constrained optimization problem, very much in the Neyman Pearson spirit for hypothesis testing. And the simplest thing to do here is just say, okay, I only will consider estimators that have zero bias, and then I will minimize the variance. So I've constrained my estimators to have zero bias. It's a now subset of all estimators, and I minimize the variance. And now sometimes there are unique estimators that do that. And many fields that were kind of developed in the 40s and 50s still have this as their main methodology. Like econometrics, much of the work in econometrics is find zero bias and minimize the variance. Okay? Best linear unbiased estimators and so on. I would say in statistics, modern statistics, that's kind of gone away. In particular, it's been noted at some point that Bayesian and empirical Bayesian procedures generally have a little bit of bias, but they often have much lower variance, and so overall they're better. They have better frequentist risk. All right, and in particular, FDR is an example of this. FDR has a bias, but it has a good variance, and we're not proving that in this class, but that's one of the justifications for FDR, other than just being having a control of alpha. Okay, so that's what I wanted to say about decision theory. That was a bit abstract. I hope the last little calculation that I did here is less abstract, but it's still kind of abstract. But we will be doing more of this during the class. We'll occasionally stop and calculate a variance or a bias, you know, when we're using the L2 loss, or we'll stop to kind of worry about trade-offs when we're using L1 loss or other losses. Okay. This is not the end all of talking about good procedures, but this is a pretty good starting place for understanding how you can make mathematics out of statistical inference. And this is very much the frequentist approach. Variance and bias have those expectations there at the bottom of the page that I'm looking at right now. Expectation for a fixed theta, okay? And all those expectations are frequentist expectations. So there's nothing but Bayesian about this, okay? And if you were doing the bootstrap, for example, you would replace all those expectations, which are gotten conceptually by looking at lots and lots of draws of the data, right? That's what E sub theta means. And saying, well, I'm going to simulate that with a bootstrap. And I'm going to replace all those E thetas with bootstrap samples and get sampling distributions and do that. And so now you're going to get a bootstrap estimate of variance or a bootstrap estimate of bias. And now you have a bootstrap estimate of the risk. And you can use that to evaluate various procedures just based on the data and this resampling procedure. Or you can try to do mathematics with this. All right, now what about the poor Bayesian? Are they kind of not doing this kind of mathematics? Well, the Bayesian does their own kind of different mathematics. We're going to be talking a lot more about Bayes starting next lecture. Professor Steinhardt is going to have several lectures on Bayes. I think of Bayes mostly as advantageous because you get to use a prior, and in some cases that's just a huge advantage. You know a lot about your problem, okay? The other main advantage of Bayes is what we call sharing of statistical strength or hierarchical models. That we've got a model that's got multiple pieces to it and they're kind of related. And so we're going to tie theta in one part of the model together with theta in the other part of the model. And that kind of provides a prior from one to the other. And they kind of strengthen each other. So this is too abstract, but you'll see this in detail coming up soon. And then if you're a frequentist and you like Bayesian, that kind of Bayesian procedure, you like the kind of stuff you get out of it, which a lot of people do, you might say, well, I'm going to analyze that from a frequentist point of view, and I'm going to maybe show that the Bayesian procedure has small variance and bias. And that's a very common thing to do. That's called frequentist analysis of Bayesian procedures. All right, and this empirical Bayes that we've been really using already in the class and we'll use more is this hybrid kind of approach where you start out with Bayesian thinking and you write down priors and models and all that. And then at some point you say, well, I don't really know how to complete the Bayesian analysis in the way that Professor Steiner will be telling you about with things like Gibbs sampling. You say, well, I'm not going to do that, but here's a quantity I can just plug in an estimator like P of D that we had in the FDR problem. All right, you plugged in that estimator now, and now you need to analyze and make sure you did a good thing. And so that analysis will probably be frequentist. And so empirical Bayes is kind of Bayesian in spirit, but analyzed with frequentist tools. Okay, so again, that's kind of abstract. Probably the most abstract will be in the class, but I just want you to appreciate that underlying this field, just like in physics, there's kind of a waves and particles. There's a real mathematics, and it's pretty solid, and it's still, all of its consequences aren't clear. But as you go on in this field, being clear on these distinctions and when someone says variance and bias and then they make a Bayesian argument, you sort of say, wait a minute, those don't go together. That doesn't make any sense. A lot of people do that kind of thing all the time. And you want to kind of call people out if they're not making sense, and you want to be able to use these tools in appropriate ways.
The purpose of this video is try to resolve some of the confusion surrounding the definitions of frequentist risk and Bayesian posterior risk. So I've already written out the definitions that you've seen on the slides or some of the previous videos in this lecture. And the main problem surrounding these definitions is that there are many different notations for taking expectations. So sometimes it's not so clear what given expectation means. Okay, so whenever you find yourself in such a situation, it's always helpful to write out the expectation as an integral. Okay, so let's do it for these two different definitions of risk. So let's start with frequentist risk. I can rewrite this expectation as an integral of the loss. And I'm going to integrate this with respect to the density on X that is parameterized by the parameter data. And on the other hand, for the Bayesian posterior risk, again, I can write this as an integral. The integrand, first term in the integrand is the same, except now I condition on X, and the density is going to be the posterior density on data. Okay, so this is not the same as the density for the frequentist risk. Okay, so another way of writing these two expectations is as follows. So sometimes we may write of data as an expectation. Okay, so here data in fixed. So X is going to be what's random, and X is going to vary according to this density. And for the Bayesian posterior risk, again, it's an expectation. The randomness is in data, and our data is going to vary according to the posterior. And I would argue that these two notations for the expectation are a bit clearer than the other definitions that we saw above. What may be ultra confusing is that sometimes when people write data in the denominator, okay, so here for frequentist risk, it is signifying that we fix the parameter data and we take an expectation with respect to the density Px conditional data. But sometimes when people write some expression like this, right, this might mean that this is taking an expectation with respect to X and keeping everything else fixed. Okay, so this is very unfortunate. These two notations are contradictory, but people do use them, and I just want you to be aware that sometimes you might see it being used in this context. Another way to think about the relationship between the Bayes posterior risk and the frequentist risk is to first consider the joint distribution between X and theta. Right, so I'm going to denote the joint density by P of X comma theta. Now we can always factor the joint density in two ways. Right, so we can either first condition on theta and then multiply this condition distribution by the margin on theta, or we can also first condition on X and multiply this by the margin on X. All right, and if you think back to calculus, whenever you want to integrate out a function of two variables, we can always make it into a double integral, right? And in it, the inner integral is always going to be the integral of the conditional, and the integral on the outside is going to be an integral of the marginal, right? And depending on the order of integration, you're going to get some intermediate quantities. These intermediate quantities are going to be the Bayesian posterior risk and the frequentist risk. So let's see that in terms of a diagram. Okay, so the quantity that we care about is this loss. Now, let's integrate in two different ways. So we first integrate on the inside with the conditional distribution X. Then this is going to give us our frequentist risk. Okay, so in the slides, we use capital R. I'm going to use small r here. You see why in a bit. Okay, and equivalently, I can integrate out with respect to the conditional distribution on theta, also known as the posterior distribution. And this is going to give me the Bayesian posterior risk denoted by rho of X. And now I can complete the circle, right? So this is the inner integral. My outside integral is going to be an integral with respect to the prior P of theta. And here, I take an outside integral with respect to the marginal on X. And because of Fabini, I'm going to get the same number, right? Fabini says you can change the order of integration, right? And so it doesn't matter which way we do it, you're going to get an integral with respect to both X and theta. Okay, so that's denotes this common number by the notation capital R of delta. Right, so this is a fixed number that does not depend on theta or X because we already integrated out these two variables, but it does depend on something. It depends on the procedure that we plug into this loss function. Okay, so this single number is called the Bayes risk. And this is the Bayes risk of the procedure delta. All right, so now how do we use these different notions of risk to make a decision? So making a decision here is choosing the right procedure, because we can have, for any task you have in mind, we can have several different procedures, and we want to know which one is better, right? So because we want to pick the best one. But depending on whether you're Bayesian or frequentist, you will want to do different things. So we call that as a Bayesian, you want to condition on your data. You want to make the best choice given the data that you have, right? And you don't want to take any expectations with respect to your data. This means that you want to minimize the Bayesian posterior risk. Okay. But it turns out that if you have a procedure that minimizes the Bayesian posterior risk, then it's also going to minimize the Bayes risk. And why? This is because the Bayes risk is an expectation or an average of the Bayesian posterior risk. So if you can minimize the Bayesian posterior risk pointwise, you're also going to minimize the Bayes risk. Okay? But this does not happen for the frequentist risk because there's some asymmetry in this. Your decision, your procedure delta always it has to take an x, right? So for the frequentist risk, you really integrate it out with respect to x in the first step. So you can no longer have this this property. Okay, so let me write out what I just said again. So if you are a Bayesian, or well, you don't have to be strictly Bayesian or frequentist, but for any given problem at hand, sometimes you want to think like a Bayesian or as a frequentist, right? So you want to find delta, or you want to choose your procedure delta that minimizes the Bayesian posterior risk. And this is going to be equivalent to minimizing the Bayes risk. On the other hand, if you're a frequentist, you don't want to use a prior because you don't want to make any assumptions on the parameter data. So what do you do instead? So instead, you're going to be pessimistic. And if you're pessimistic, this means that you're going to assume the worst possible risk. And so you're going to assume that the data parameter that is the truth or that you're trying to estimate is the one that maximizes the risk. Okay, so precisely you want to choose delta that minimizes the so-called worst case risk, i.e., this would be the maximum of all data in the parameter space of the frequentist risk R of data. Okay, and here recall that the frequentist risk is a function of data, but implicitly is also a function of your procedure delta. Okay, so to make things clearer, let's write in delta as an input into the frequentist risk. Okay, so to recap, what we want to do is to choose a procedure that minimizes this worst case risk. Let's call this delta star. And this procedure has a name. So this is called the minimax estimator or procedure, right? Minimax because it minimizes the maximum risk. Okay, so two different perspectives and two different procedures, or well, two different perspectives and two different ways of choosing procedures, right? Depending on whether you're frequentist or Bayesian, you're going to end up thinking of different procedures as being the best one.